Hello everyone, welcome to the video for Lecture 14, Section 1. This video is the first of several videos about actuators. In the videos, I will talk about key characteristics of relays, solenoids, solenoid valves, stepping motors, variable speed drivers, thermostats, and timers. Before we talk about their characteristics, we need to learn how they are included in the closed-loop block diagram and the overall transfer function for a time-dependent process. Here is the block diagram of our generic closed process. The red circle highlights the actuator, which is going to be described by the transfer function G2. The actuator is different than the other closed-loop process control elements because it has two inputs. One input is PS, which is the output of the controller J1, which we talked about in the previous class. The other input is the manipulated or controlled input. The controlled input can vary depending on the process. For example, the fluid heater process I talked about in section 4 and 5. The controlled input was the electrical energy used to heat the fluid in our fluid heater. In mixing problems, the controlled input will often be the flow rate of some chemical that is being added to the tank and mixed. In fluid flow problems, the controlled input probably will be some fluid flowing through the tanks. The output of the actuator is labeled as QS. QS describes the amount of controlled input that is actually entering the process element G3. This means we will think of PS as a control signal which provides information to the actuator, but no material. So PS tells the flow valve how far to open, or it may tell the relay how long to keep the electric heater on to heat the fluid. So be sure to note that there is commonly a units change between PS and QS because the units associated with QS depends on the controlled input. Here is a list of actuators. In other Lecture 14 videos, I will talk about them and some of their key characteristics to consider when selecting as an actuator to use. You will see some of these actuators in one of the labs. For this class, we will model actuators with a first-order transfer function relating the actuator output, QS, to the controller input, PS. So the transfer function will be kV over tau v times S plus 1. In many cases, the actuator time constant tau v is very small relative to the other process time constants that we can model the actuator as a constant gain, kV. We talk about the gain of a transfer function in section 7 of the course packet. So if we assume tau v, the time constant of the actuator, is much smaller than the time constant of the process, tau p, we can combine and simplify the two elements and use one transfer function that relates the process output, CS, to the controller output, PS. For more details, please see page 15-2 of the course packet. One of the things that you need to be able to do is find the actuator gain. The problem is this course uses both electrical control signals and pneumatic control signals. Newer processes are using electrical and digital control signals, but you may work with equipment that uses pneumatic control signals. Electrical signals are usually use current ranging from 4 to 15 milliamps. Pneumatic control signals are usually air pressure. The ranges vary. In most cases, we will assume that the relation between the input control signal, whether electrical or air pressure, is linearly related to the actuator output. For our first examples, Let's assume that we have a valve described by the linear equation given. The expression given is Qm equals to 8 times Pa minus 32. This means that the valve flows goes from 0 to 88 milliliters per second, as the input signal goes from 4 to 15 milliamps. So if the control signal is 4 milliamps, the valve has 0 flow, and if the control signal is 15 milliamps, the flow is 88 milliliters per second. Now we are told that the steady-state control signal for the process is 8 milliamps. We can use the information to find the steady-state flow rate through the valve. In this case, the steady-state flow rate Qs is 32 milliliters per second. Now we take the difference between the valve equation and the steady-state valve equation, relating the control signal PA to the valve flow rate Qm. By taking this difference, we create difference that we can use to define deviation variables. Using the deviation variable, we find that the flow deviation variable, capital Q, equals to 8 times the control signal deviation variable, capital P. We can take the Laplace transform and find that Qs over Ps equals to 8. So the valve gain is equal to 8. Sometimes you will be given two data points and need to find the linear relation. The 2 points can be used to write two equations with two unknowns, A, the slope, and B, the zero intercept. For this example, we are given that the flow is 0 cubic meters per second if the pneumatic control signal is 20 kilopascal, and the flow is 0.001 cubic meters per second when the pneumatic control signal is 100 kilopascal. We will assume that the relation between the actuator flow rate and the pneumatic control signal is linear, given by QV equals to A times the control signal pressure PA plus B. A is the slope. With the two data points, we write two equations. Now we have two equations with two unknowns, A and B. Solving for A and B, we find that A equals to 1.25 times 10 to the minus 5 cubic meters per second kilopascal, and B equals minus 2 times 10 to the minus 4 cubic meters per second. Based on the previous example, you can see that the gain of this valve is 1.25 times 10 to the minus 5. Before we wrap this video, let me remind you again that many actuators will produce a unit change between the input control signal PS and the actuator output QS. For the last example, the control signal was pressure, kilopascal, and the output was flow rate. With relays, you will learn that a small control signal can control a very large electrical input. This means that relays can have very large gain values. This brings me to the end of the lecture 14 section 1 video. The next video will cover relays. Please write down any questions you have and bring them up in the class or lab. Thank you.